All right, so good morning, one and all. Now we are making these set of videos to throw more light on the labs that we have been doing so that we can adequately prepare for our lab exams. Now, this is week 2, and then we are learning the use of weighing equipment. We are learning how to determine uniformity of weight of tablets, then calibration of burettes. Good. So the first one, use of weighing equipment. Now, the main weighing equipment we will use in the lab is called the analytical balance. Now, we are saying it is very delicate. So the first statement, now it means you have to really take care of it. And then it possesses a high degree of sensitivity. That is, it can measure very small weight, right? It can measure very small weight. If you talk about your sensitivity, we are talking about your ability to measure or detect very small weight to a higher accuracy, right? And then it happens that if the weighing balance has a sensitivity of, let's say, 1 gram, right? If anything less than 1 gram, it cannot really measure it to a higher accuracy. But then anything greater than 1 gram, it can really measure it to a higher accuracy. So that's what we mean by sensitivity. And then if we say it has a high degree of sensitivity, it means it can measure something which is very small, right? It can measure very small masses. That is what we mean. Good. Now we are saying that the weighing of substance can be done directly. So it directly means that you put your weighing board there on the balance and then you tie it. When you tie it, it considers it as 0. So then the next weight that will come in will be the true reflection of the substance inside the boot, right? And then we can also weigh by difference. By difference, we take the weight of the boot, right? And then we add the substance to the boot, take the weight of both the substance and boot. And then the weight of the substance will be equal to the combination of the weight of the substance in both minus the weight of the both, right? Very simple. So that is how we determine we can measure weight by difference. Good. Now, care of balance. We are saying that material spilled on the balance pan or base must be cleaned up immediately. So that's what we are saying, right? Sample must not be weighed directly on the pan. We don't put anything on the pan here. You put it in the boat and then you weigh, right? A stopper container must be used for weighing liquid or volatile, the liquescent and hygroscopic solid. And so if the liquid is volatile, that is if it can evaporate easily, if it's a deliquescent solid, that is if it can absorb water to form a solution, or it is hygroscopic, that is it can absorb water just to have water of crystallization, which might affect the weight. We are saying that measure it in a container that is covered or stopped. Very simple. Now we are saying that hot objects must be cooled to room temperature before introduction to the balance. Now, if the material is hot, it can cause expansion in the metals in the machine, which we don't really want to happen, right? So we are saying in essence that make sure the hot object is cool to room temperature before you weigh it in the balance. Now, the door of the balance must be closed when the final weighing is being made. So you see this one is covered, right? Always close the door before you make the final reading. The next one, the balance must not be overloaded. Now, for any balance we have, it has a maximum, right? Good. And so they will always write the maximum of the balance, the maximum load it can take here, right? Maybe 10 grams. And so if you go and put something which is 50 grams on this balance, it will break the balance. You get it? So always make sure your weight is below the maximum. Now, we are saying the balance should always be placed on a solid concrete surface just to prevent it from falling down and then breaking. Now, we are saying that exposure of the balance to corrosive atmosphere must be avoided. The balance has metallic surface and all. If you expose it to corrosive surfaces, it will corrode, right? That is what we are saying. The last note here is that keep the weighing area or room clean. Now, we can be asked to give maybe 3 ways of caring for our balance. So these are the answers to those questions. But next one, determination of the uniformity of weight of tablets. Now, by the name here, we want to see whether the tablets are uniform. Uniform means they are the same, right? Now, how do we do the tablets? Always tablets would have an API. The API is what we call the active pharmaceutical ingredient. And so if you take a tablet of paracetamol, 500 milligram, the API or the active ingredient is the paracetamol itself. But then trust me, the weight of this tablet is beyond 500 milligram. The idea here is that it is not only the active ingredient that makes the tablet, but then it's a combination of the active ingredient and what? The excipient and the excipient. And so there's a scenario that if we are making 250 milligram of paracetamol, and then we are making 20,000 pieces of the 250 milligram of paracetamol, what do? Now, we find the total milligram of paracetamol we need, right? And then that will be around, let me check the number, 5 million milligram of paracetamol, right? Good. Now, this 5 million, we will not divide it into 250 and have each of the tablets made. No. We will take all the 5 million milligram of paracetamol and mix it with the appropriate excipient and then divide them or compound them into different tablets. Now, the mixing here should be uniform. We are expecting it to be uniformly distributed. That's the API should be uniformly distributed, such that if I divide them into the 20,000 tablets, I'll get each of them containing the 250. Now, the only way I can check that each of them contain exactly the 250 is by doing what? It's not the only way. One of the ways is uniformity of weight. Now, when I do uniformity of weight and then I realize that all of them are within range, it means the person taking the tablet is assured that he's taking the right dose of the drug. If it happens that one tablet weighs, let's say, 500 grams, another one weighs 700 grams. Now, the one taking this tablet and the one taking this tablet, definitely the paracetamol in these ones are different. That means they are taking different doses, and sometimes the doses can actually be toxic. You get it? So, in order to check whether the patient is taking the right doses, we do uniformity of weight. Very simple. So you can read through this one, is the same idea. Now we are saying that determination of the uniformity of weight is routinely carried out during tableting process and after production. So during the tableting process, we carry out uniformity of weight. After production, as a quality control, we also carry out uniformity of weight. Now, how is the process done? So randomly, we pick 20 tablets from any batch, right? And then we measure and record their weight. Very important. Now we find the average weight of the 20 tablets. I think this one should be 20 per the knowledge in my head. So we find the average weight of the 20 tablets. Now, this is the standard. We are saying that not more than one tablet should deviate from the average by a percentage greater than shown in the table. Let's go to the table and then I will explain these statements. Good. So we are saying that if we are expecting the weight of the tablet, or the weight of the tablet is around 80 milligram, right? Then the expected deviation should be plus or minus 10. That is, if you are 70 milligram, you are accepted. If you are 90 milligram, you are accepted. So between 70 and 90 is quite accepted. Now, we are saying that if it's more than 80 but less than 250, then we are accepting 7.5. So the same way, if you are lesser than maybe the given range is 200. 200 is between the 80 and then the 250, right? If you happen to be 192.5, you are accepted. If you happen to be 207.5, you are accepted. So anything within this range is accepted, right? Good. Then if you are more than 250 or 250 or more, then we are saying, assuming the tablet is 250 milligram, right? Any tablet that is 245 is considered. Any tablet which is 255 is also considered, right? It falls within the range. It is part of the, or it falls within the percentage permissible, right? Now, these ones are just citing examples, because these are not actual values, they are percentages. So I'm just doing the rough estimate here. Ideally, before you find, you have to strike the percentage or find the percentage of, so maybe 10. The permissible range is 10. So 10% of 80, that's 10 over 100 times 80. This one, so it will be 8 milligram. It will be 8 milligram. And so what we are saying here is that ideally, It's either you fall below it by 8, that is, it should be 72 to 88. Now, this is the accurate range that we are talking about. So if you fall within any of these range, it is fine, right? Good. Even that, we are saying that within among the 20 that we have selected, not more than 2 of them. This is not more than 1, this is not more than 2, but then let's take them not more than 2. So if it happens that 3 of them fall outside this range, then we can see that the tablets are not uniform. So the maximum that can fall outside this range is just 2 tablets, right? Not more than 2 should deviate from the average by a percentage greater than that which is shown in the table. Then we are saying that none of the tablets should deviate by 2 times of that percentage. So assuming the one I've calculated, we are saying the deviation allowed is 8 milligram. So you can actually be between 72 and then 88, right? And then the normal thing is saying that not more than 2 should be outside this range. Good. Now, we are also saying that if, let's say, 19 of them fall perfectly within this range, and then just one of them is maybe 16 times lesser than the 80 milligram or 16 times more than the 80 milligram, then that bar 2 is disqualified. So none of them should be more than 2 times. So anything more than 60 milligram deviation should be disqualified. That means that batch is not uniform. That is what we are saying. Very simple. And so whatever you do, when you get your deviation, you come and compare it to the standard and see. Now, this is how the experiment is carried out. You first of all need the weight of the empty boat. We told you that do not measure the weight directly on the balance. So you always put in the boat and then you measure. Now, when you are putting it in the boat, it means you are measuring by difference, right? If you are measuring by tiring, you don't really need the weight of the boat. Are we following? Good. Then you also have to measure all your 20 tablets plus the boat, right? And then you also record your weight. Good. Now, we are seeing that the weight of the boat recorded. Now, if you want to find the weight of each tablet, right, the weight of each tablet, we told you that we have to measure each of the tablets singly. So the weight of each tablet will be the weight of the tablet plus the boat minus the weight of the empty boat, right? That will give you the weight of each tablet. Good. So what you weigh directly, if you put each tablet on the balance, you get the weight here, you get the weight there. And then if you want to find the weight of just the tablet, you subtract the weight of the empty boat from it to get the weight of just the tablet here, right? Good. Now, the next thing is that you find the deviation. The deviation will be the individual weight of the tablet minus the average weight of the tablet. Now, how can we get the average weight? After getting the weight of the 20 tablets, right? The 20 tablets, you can get it by subtracting the value here, assuming it's x minus the weight of the empty boat. How we follow? So you get the weight of the 20 tablets and then you divide by 20. So the total weight of the 20 tablets divided by 20 will give you the average weight of the tablet, right? Good. And then for us to find the deviation, it's the individual weight minus the average. So assuming the weight here is 5, right? And then the average was 5.1. Then it means the deviation will be 5 minus 5.1, and that will be negative 0.1. Always the deviation, you bring a sign. So if it's a positive, you bring a positive sign. If it's a negative, bring a negative sign in front of it. Very simple. Very simple. Good. Now, the next thing is that you find a percentage deviation. Now, how do you find the percentage deviation? The percentage deviation is equal to the deviation over the average weight times 100. So the average weight has already been gotten from here. Now, if you take this deviation, you don't consider the sign. So you just take 0.1 over the average weight, assuming it was 5.1, right, times 100. Now, times 100 will give me the yes, if I multiply by 100, I'll get the percentage deviation. Now, after getting it, we are saying that no more than 2. Okay, the tablets we consider in the experiment in the lab was 500 milligram, right? The 500 milligram will fall under this section, 250 or more. So we are saying that deviation should not be more than 5%. And so if it happens that all of the values here are less than 5%, then we have passed. If one value here is, let's say, more than 5%, then we have passed. If two tablets here, if two of these ones are more than 5%, we have passed. If three of them are more than 5%, then we have failed, because we are saying that not more than two of the tablets should deviate by a percentage greater than that which is provided in the table. Are we following? Good. Now, if it happens that all of them have passed, but one of them is, let's say, has deviated by, let's say, 11%, then we have failed, because we said none of them should deviate by more than 2 times the permissible deviation. Very important. Next thing, calibration of a burette. Now, we do calibration to actually verify whether our equipment is working well, right? That is why we do calibration. So usually if you take your burette, right, it has values on it and all, but then we know that sometimes even in the presence of change in temperature, there can be expansions, and then the volumes delivered might be different from the volume stated on the material. So it necessitates that before any experiment, we calibrate the burette. Let's go to the experiment. Now we are seeing that calibration of glasswares like burette and analytical equipment is required to ensure delivery of consistently accurate results when used. Different grades of burette exist, but then we use the grade B in analytical laboratory. Now, burette often expands with increasing temperature, causing them to deliver volumes that may deviate significantly from expected. Right? That is why we have to actually calibrate to make sure that the volumes we are getting are that which has been stated. Good. Now we are saying that it is therefore important to calibrate burette to determine the actual volume of the liquid. Right? So the fact that we have moved it from 0 to 1 doesn't mean it has delivered 1 ml. We have to actually calibrate to make sure that we know the actual volume that is delivered during analytical work or titrations. Now we are saying that before calibration of a burette is carried out, there are 2 main tests that we do before we do the calibration. So these can be called preliminary tests that we do before we actually come and do the calibration. Now, if it fails these preliminary tests, most of the time it is not important to do the calibration again, because definitely it might fail. You get it? Good. Now, the first test is called the leakage test. Contrary to the name, leakage test is actually testing for your ability to hold water and prevent leakage. Right? Yes, so maybe it's not contrary or it's within line, but then that's the idea. That's what do? We fill or adjust the volume of the water to the 0 mark in the burette, and then we close it, and then we allow it to stand for 10 minutes undisturbed, and then we are expecting the burette tap to hold the liquid such that less than half of a deviation should fall. If we have the liquid falling more than half of a smaller deviation, then it has failed the leakage test. Next one, the delivery time. Now, the delivery time would test how the burette will allow liquid to flow through it within a given time. And so for any burette, there is a stated delivery time there, and then usually the delivery time that we compare it against the manufactured delivery time to show that it is still consistent with the quality of production. And so what do? We fill the burette, adjust it to the 0 mark, and then open it fully while simultaneously starting a stopwatch. And then we check the time where the water will fall to the lowest mark. The lowest mark on the burette is actually 50. Yeah, so where it reaches the lowest mark, and then we check the time it got there. If it's 10 seconds or 50 seconds, we compare it to that which is on the burette. Now we are seeing that the time should closely agree with that which is on the burette. Should it happen that it doesn't agree at all, then we can see confidently that the burette is not consistent with the manufacturing quality, right? Good. Now, should It passed the first two, then we move forward to the calibration of the burette. So we are now starting the experiment proper. Now, what do? We are saying that you clamp your burette in an upright and fill with distilled water. Now you weigh an empty conical flask. Then you run 1 ml of a distilled water into the flask, and then you weigh. You take the weight. You add a further 1 ml, you check the weight. You continue adding 1 ml and checking the weight till you come in total 15 ml. Right? Good. Now we are saying that place the beaker on the bench and measure the temperature of the distilled water. So we are measuring weight. Now we are measuring temperature, right? Now, why is temperature necessary here? The temperature will influence the density. So we are mentioning temperature because we are aware that temperature will influence what? The density of the water. Good. Now we are saying that we use density table below to extrapolate or calculate the actual volume. Now, depending on the temperature of the water, assuming it is 30, then we take the specific volume provided in the table. If it's 28, then we take this density, right? If it's 22 degrees, then we take what? This density. Then so depending on the temperature of the liquid, then we choose the density. The idea is that temperature affects density, right? If you increase temperature, what do? You decrease the density. And so if you observe, this is actually the inverse of density. So let me explain these two terms. So what we have here is called specific volume. Now, specific volume from the unit here, this is no magic. From the unit here, mole over gram is what? Volume over mass. Volume over mass. Now, we have another term called the density or the specific gravity. Specific gravity. Specific gravity will be gram per mole, and that will be what? Mass over volume. So depending on which one you are given, you should know where you have to go to. Very simple. Now we're given specific volume, and so you realize that the trend changes a little bit. Good. Now, after choosing the correct specific volume relating to the temperature, the next thing we are saying that you plot a graph of the actual volume delivered against the volume read from the burette, or the volume delivered by the burette. So let's digest this. It will help us to draw the graph better. Now, what do we need? Before we do anything, we need the weight of the empty conical flask or beaker, right? Good. Now, the mass of water delivered at each stage will be the weight of the flask, including the weight of the water, minus the weight of the empty beaker, right? Good. Now, for us to find the actual volume of water, because the scale is giving us mass, for us to convert the mass to volume, they give us specific volume, which is equal to volume over mass, right? Now, if I make mass the subject, I will have, sorry, if I make volume the subject, I have volume being equal to specific volume times the mass. So this is what we are doing here. And so we are saying that for us to convert the mass to the volume, it will be equal to the specific volume times the mass, or the weight of the water. Good. Now, we will use that to find, so if here we had, let's say, 5 or 2.50 grams, and then assuming the weight of the flask was 1 gram, 1.0 gram, it means the weight of the water here is what? 1.5. That is the 2.5 minus the 1.5 gram. Now, after getting the 1.5 gram, we have to convert that to what? To the actual volume. We have to change it from mass to volume. So that would depend on the temperature. Assuming the temperature was 28 degrees Celsius, that means the density I have to consider is 1.0038. Good. Now, my volume now will be equal to the 1.5 grams times 1.0038. Now, this one will give me the actual volume, right? So I'll fill this table, and then my plot should have the actual volume being plotted against the expected volume on the x-axis. So that is what we have here. Actual volume against expected volume, right? Good. Now, you plot it. You are expecting a straight line. Sometimes the lines are not really aligned. So then you draw the line of best fit. You draw the line of best fit. Now, when you draw the line of best fit, you find the slope of your line. The slope of your line is a very important parameter because it will help you to find the actual volume used in the experiment. So after getting your slope, you forget about any other thing you had from the experiment and focus on the slope, because any other subsequent criteria or measurement or parameter should be based on the slope. Now, there's a standard here we have to pay attention to. The standard is saying that a grade B burette should deliver 1.00 mil and 2.00 mil, two accurately to 0.02 mils. Now, it means that if I'm delivering 2 mils of, if I'm saying I'm grade B, I'm delivering 2 mils, it should be within 1.98 and 2.02. If it falls outside this range, you are not a grade B. You are not grade B. It follows 5 mils should be to an accuracy of 0.03, 10 mils should be to the accuracy of 0.04, 25 mils should be to the accuracy of 0.08 mils. Are we following? Good, good. So now we come using the slope we have gotten, we'll come and draw this table and compare it to the standards that were given to us. Now, from the first narration of the standard, you should be able to find, I did this example in the previous one, so you should be able to draw these ranges. But now, we are saying that the actual volume now is equal to the expected volume times the slope. And so, if we take the 1 mil times the slope we had should give us the actual volume that it was able to deliver, right? Good. Now, once we get the actual volume, assuming it was 1.10, then the deviation will be the difference between this and this, right? The difference between this and this. Now, if you subtract this, the 1.1 from the 1, you get negative 0.1. So negative 0.1. Now, this deviation, right, it has deviated from it negative 0.1, but the permissible deviation was 0.02. It means it is not a grade B, because a grade B should strictly have these ranges being complied to, right? So no matter the values you have, the actual volume, you find it by multiplying the expected volume, multiplied by the slope, and the deviation is the actual volume minus the expected volume. The actual minus the expected volume. So we take the actual, you subtract the expected from it. So in this example, if I'm following this formula, it will be 1.10 minus 1.0, and that will be 0.1. That will be 0.1. That is that for that. Good. So I think if you use this example, you can go through your slide or your lab manual and then really understand it. Thank you very much for staying tuned.